All right, so in this video, I'm going to have the derivation here of the momentum integral boundary layer equation, and and then that relates the wall shear stress to the boundary layer thickness and how it changes along the plate edge. And so, what we have drawn here is the boundary layer. So first of all, we just have a flow of a flat plate, coming with a uniform upstream velocity coming over the plate. And then later on, we have some velocity profile that is arbitrary right now. And what we can then use this is through the drag on the plate, obtain an equation that relates, well, the drag to the thickness of this boundary layer, and then therefore to the wall shear stress. So the diagram here, it's got lots of colors and lots of arrows, but we have a plate drawn in purple with the velocity profiles, again, assuming this has to be given or approximated, and we have the Blausius solution, which is the exact solution for a laminar flow, but perhaps it's some just approximated velocity profile too, and there's a homework problem on that. And then our boundary layer, we know, grows as the square root of x. We have drawn on here a control volume that we'll be using here in a bit. So in the dotted green line here is our control volume, or it's actually the control surface where everything inside is the control volume. And so then if this is control volume, we need to think about all the forces acting on here. And so we have drawn on here the drag force, which is the integral of the shear force over the entire plate. Okay, so that orients everything. Our x direction here is along the plate. Our boundary layer edge is in the red dashed line, and the control volume we'll use is in the dotted line. And the reason it's like this is because we're just following a streamline here. It's some we don't know exactly where it is, but I've just drawn it right here, and then it reaches the upper edge of the boundary layer here at the right side of the plate. Okay, and we know from our earlier analysis that the wall shear stress should go as 1 over the square root of x. Assume also that the plate width into the page is b. Okay, so the way we do this is that we drew our control volume. We'll do the momentum equation, the x direction over this control volume. And so again, we have the sum of the forces in the x direction balanced by the momentum fluxes through the control surface. So this is at 1 in the x direction, the momentum flux through here, and then at 2 we have the momentum flux there. Well, we have pressure forces here, but they're gonna cancel, right? So everything here is at atmospheric pressure. For flow over a plate, external flow, as long as it's flat like this, we have constant pressure throughout, and so those will just cancel. So the only force is just the drag, which is in the negative x direction. Our momentum flux terms, u dot n, this is an inflow, so n is always pointing outward, or the unit vector here, n is always outward, u flows in, so this is a negative u, negative big U upstream velocity here. And then the velocity itself is just positive u. So that's why, and then integrate that over the area here, which is some height h, and let's see, and into the page we have b. Okay. We then do the momentum flux out the right-hand side here, the outflow region. So u dot n is now positive, and it's going to just be the local velocity u, the velocity profile with y, and the velocity is just u itself. So here we have the integral over from 0 up to delta of u squared dy, right? Okay, so that's our momentum equation. We can then use continuity with the momentum equation, as we did back in chapter 5 or whatever that was, to then relate these two, because we know that this is a streamline, so there's no flow through our control surface. So this is a streamline, that control surface there. Okay, so continuity just says we'll integrate our velocity over the area, and we get the volumetric flow rate through 1. And that should equal the volumetric flow rate through 2, because there's no flow through the control surface in any other place. So here we just have u over the area, it's just b times h. And here our area, well, we're integrating over the area of b, and then from 0 to delta, just the velocity itself. All right, so this now is we get UBH and then times this integral. Let's multiply by rho U to make it look just like this term. We get rho U squared BH is now written in terms of this integral, rho B, and putting the U on the inside here, so that when we plug it into here, we can just say the drag force is just equal to the density times the thickness into the plate, and then this integral, which, if we compare this to the boundary layer momentum thickness quantity, this is just that quantity times big U squared, times upstream velocity squared. So therefore, we can make the final statement here that the drag force can be related to, well, the density and the thickness into the page, but the upstream velocity squared times the thickness, the boundary layer thickness, momentum thickness. Now this is a function of x. So this is the total drag on the plate up to some arbitrary location x, right? This is really the drag for the first x part of the plate. So it's the plate drag up to x. We note that as x increases, we know that our boundary layer thickness increases, so therefore our total drag must increase. As the plate gets longer and longer, we go further along the plate. So we can then relate this to the wall shear stress also, because we know that the drag goes is just the integral of the wall shear stress over the area of which it acts. So we're going to just integrate on this wall shear stress also up to that same x location. And here the integral over the area again is just going to be d into the page, and then an integral in that x direction up to x. So we have an x prime here. And tau, wall shear stress is also a function of x itself. So another way to say this relationship is that the change in the drag with x is just the thickness into the page times the wall shear stress, where, again, these are both functions of x. We also have, from our last relationship, we could also take the derivative of this with x. So then we have d, the change in the drag along the x direction is also related to the momentum, the derivative of the momentum thickness in x. So with these two quantities, we can then relate the wall shear stress to the ever-increasing thickness of the boundary layer. So this says that the wall shear stress, once we solve it here, the wall shear stress is then balanced by a growing viscous region. So there's a region that continues to grow and grow and grow, and that is our boundary layer, and that is what, for external flow, balances the wall shear stress. So if we summarize, we have our momentum thickness defined this way, we have our wall shear stress defined this way. Once we know or have an approximate velocity profile, we can then relate the two with this, the momentum integral boundary layer equation here. Okay,